So we are starting the afternoon session, and the first speaker will be Arkady Tseytlin. We'll talk about quantum superstrings.
Well, thank you. Thank you to the organizers. Thank you, Joe, to give us an occasion. So I'll start. That will be my kind of technical side, technical part of the talk. But I'll start with some remarks about, well.
Doesn't switch.
Yeah, some remarks how I got to know Joe. And this is a bit of history, ancient history now. So I met Joe first in the library, and actually in the library like 37, I guess, years ago, when I was opening Nuclear Physics, recent issue, and that was the time when we still were reading journals. And I discovered that paper. I was actually surprised. Probably I didn't read the preprint, or I missed it, or it was too technical for me. I didn't appreciate what was done there. But anyway, there was this paper. And the reason why I paid attention will become clear in a second, but let me just say what was done in this paper. It's about hydraulic string on an orbifold. And you can consider an orbifold which breaks supersymmetry, say, to n equal 1. And you can ask a question, how do you see the beta function of the resulting super-Young-Mills theory plus matter? In this particular case, that we gauge group, which we discussed in this paper, like E6 times what something, SU3 times E8. Yeah, so you break E8 times E8 to that group, and then there is some matter, and then you compute beta function. How do you get this beta function from string theory on a torus? So you need to do this computation on a torus. What Joe did, he considered three-point function of gauge bosons, and now it's tricky because you need to go off shell, because naively three-point function will be just zero if you put everything on shell. And that is done by relaxing momentum conservation. So you go a little bit off shell, and then what you find, you need to take alpha prime to 0. That's kind of logic that to recover field theory, you need to take alpha prime to 0. And you need to watch for logarithm alpha prime, because alpha prime plays the role of cutoff in string theory. Now we know about that. Familiar. Yeah, we are familiar with the fact that alpha prime plays the role of proper time cutoff effectively. So if you get log alpha prime times ki kj, where k is momentum, you differentiate of alpha prime, that's how you get beta function. And that was what Joe demonstrated in this paper. So essentially the question is how to recover quantum corrections in field theory from quantum, say, one loop, in this case, torus computation in string theory. That paper was, well, let's try to see when. This is Nuclear Physics 298, July 1987. That same issue of that Nuclear Physics, a little bit later page, but submitted month before, was our paper with Ruslan Mitsayev, who was my first and best student at that time. And the question which we addressed in this paper was more or less the same. How you recover divergences in field theory starting from string theory. So we considered much simpler examples, but the idea is more or less the same. You need to take alpha prime to 0, you watch for logarithms of alpha prime, but also inverse powers of alpha prime. That will give you power divergences. And one of the particular examples is to see how you recover the fact, kind of which was first, I think, observed back in 1983, that if you take Young-Mills theory in d dimensions, just bosonic, reduced to 4 dimensions, the beta function in that theory which just has Young-Mills plus a joint scale, it's actually proportional to D minus 26. But in this paper, we kind of understood why D minus 26 appears in this case, and that's to start with an analysis diagram in open string theory, bosonic string theory. You need to generalize the modular measure in a way which effectively goes back to operator formalism and related to how Lovelace first discovered that if you take D to have no cuts in the non-planar open string diagram, you need to set D equal to 26. But if you relax that, you can see that the corresponding divergence in field theory will be precisely proportional to F mu squared and D minus 26. Similar computation in supersymmetric Young-Mills theory will give you coefficient D minus 10. If you just have Young-Mills in D dimensions, super Young-Mills reduced to 4, you get D minus 10. And then we also considered all sorts of other examples where you have power divergence in field theory, like Young-Mills, super Young-Mills, or Young-Mills in say 10 dimensions. You'll have F4 term, which is quadratic divergence. And you see this as a 1 over alpha prime F4. So anyway, both these papers are kind of morally related. They both got a little bit of attention. Each has over 100 citations. And that's how I learned to pay attention to what Joe is doing. That was his actually second paper. His first paper was with, it's the wrong way, with Joe Harvey about open strings on orbifold. That was his second paper. And then comes his third paper. And so that paper, I read the preprint, and maybe Joe doesn't remember that. But that's a paper, well, I'm running out of time, so I'm not going to tell you what is done in this paper, you can read. But the point is, yeah, so this paper is not that important. And I think it has just 10 citations, but it's about two-point function of gravitons in bosonic string theory on a torus. So you have dilaton tadpole, you expect square root of G appearing, times exponent of dilaton. So square root of G contains h mu, so you can discover that by taking two-point function of gravitons. Anyway, this is all not terribly important. What is important, this computation is subtle. You need to have cutoff, regularization of the world sheet, regularization of Möbius volume. Well, anyway, so that led to, yes, I was founded like a few weeks ago, going through my old papers. So that was the, Joe was on his first postdoc in Florida, and I actually read his preprint, and I got very excited because I was doing similar things at that time. And I wrote him a letter. This is a draft of the letter. That was pre-email. So I wrote it and then gave it to the secretary, like a three-page letter. I gave it to the secretary to type and send to Joe, and he was very generous to actually have a comment in his paper, which was, I think it was submitted later, added to the original version. So he thanks me here somewhere and adds a comment about alternative regularization. Anyway, so this is all ancient history, but that's how we sort of, how I became aware of him and he became aware of me. So later on, I don't remember when we actually met in person, maybe in '98 in Santa Barbara, maybe. Probably, or '95 at Strings in Los Angeles. Maybe that's maybe another. But anyway, later on, we kind of in recent times, relatively recent times, we collaborated on 3 papers. One was about Landau-Lifshitz model, how you relate string theory to spin chain on gauge side by considering Landau-Lifshitz description, plus you take certain limit on string side. I have no time to explain this. There were 2 papers on that, which are not terribly remarkable, but the third paper was more remarkable, and it also has 100 citations plus. So that was with Alan Tirzio, who was a postdoc at the time at Ohio State, and that's about kind of elaboration on observation of Hoffman and Moldavsky about giant gravitons. you can have this generalization of the giant graviton limit by starting with semi-classical string states with several spins and taking one spin much bigger than the others, which still can be large. And then you recover the same more or less formula, which square root formula for the energy as for the giant graviton. And Joe understood also how to get this from kind of finite gap description of semi-classical solutions, etc. So yeah, I think this paper is of interest, but anyway, let me get back to the subject of my talk. This is about how we can have, how we actually understand AdS CFT as correspondence between two sides. One side being pretty much well understood at weak coupling, and then extrapolated to strong coupling using various methods. We have some exact results, but the other side, which is string theory or superstring theory or membrane theory in the case of ABGM, kind of not at the same footing for many reasons, but in particular, these models, both Green-Schwarz and M2 brane theory, they are formally non-renormalizable. So M2 brane theory more non-renormalizable than Green-Schwarz, but still one may wonder whether these theories actually ultraviolet finite, etc. But if that is the case, then what should we do actually? How we compare both sides? So one point of view, which is not very productive, is just to say that, well, these models are kind of effective few theories. You just look at collective coordinates of some soliton, and that's symmetries tell you what are the actions. And indeed, the actions themselves are not randomized. Like tension is not randomized, but there could be higher order counter terms. But we don't really know how to find these corrections to these actions. For example, in the case of D-brane actions, we know that there is an open string picture which tells you what are the corrections, but not in the case of Green-Schwarz fundamental string or membrane action. So we kind of need to understand better what are these theories actually telling us. And hope could be that, like in the Green-Schwarz case, there is a hidden symmetry like integrability. Analogy is TT bar, but what would be that in the case of membrane theory? That's the big question. That's what I'm going to kind of review, what we know about this semi-classical computations done from Green-Schwarz membrane theory. And the question would be how we're going beyond one loop approximation. So classical contributions in one loop at strong coupling are indeed matched by Green-Schwarz and membrane computations, suggesting that these theories actually have the right degrees of freedom and the right structure to describe the dual field theory at strong coupling. But what happens beyond leading order? So that will be more or less a question. And I'll emphasize a few cases where there's a need for two-loop computations to understand what's going on. And let me first say what we know about going beyond one-loop semi-classics. And that's the example of cusp anomalous dimension at strong coupling. There is this function f of lambda. And the first two terms are just JKP classical contribution, which is square root of lambda. And then there's one loop correction, A1. And the two-loop correction was actually also computed directly from the Green-Schwarz diagrams in Green-Schwarz theory in AdS 5S5. And the result for this Catalan constant was matched exactly with what follows from integrability from BES equation, essentially. So that's example. And similar computation was done from Green-Schwarz string in AdS 4 CP3. Again, it's result is ultraviolet finite, matches the ABGM value, but that's it. No other Green-Schwarz computation were done. Two-loop computation were done so far, and nothing for M2 brane. So that's my plan. I'll give some examples of what was done at classical and one-loop level, and then I'll discuss something else, which would be not directly related to AdS CFT, but rather flat spaces matrix on Green-Schwarz, on long Green-Schwarz string, and on infinite membrane. So example which we are very familiar with, it's half BPS Wilson loop, and there is the localization result, which is just Laguerre polynomial expression. And if you expand it at large n, the leading term is the famous Bessel function of these guys, Ericsson, Simonov, and Zaremba. So this I1 expanded at large lambda gives exponent of square root of lambda, which is has natural classical string action description. There's a prefactor, which is one loop kind of contribution. But then if you look at next order, that will be two-loop string computation. Two-loop result, which is one over string tension. So that's something which we are trying to actually compute now and to try to reproduce this coefficient. So that's one example which would be beyond the lead in order to see whether the string computation gives finite result and precisely that constant. So similar story in the case of ABGM theory, where there is, again, at large n, there is this Airy function ratio for the Wilson loop. There is a prefactor, 1 over sine prefactor. And in two different limits, like M theory limit or string theory limit, you can see what are the subleading corrections. So as I'll say in a second, and in fact that was discussed in earlier talks, there is a classical contribution, which again will be classical string area. Then the membrane area, there is a prefactor, which is one loop membrane contribution, but subleading term will be two loop membrane contribution, and similarly two loop string computation contribution if we look at string regime. So again, these two results presumably should follow from Green-Schwarz and membrane theory, and it would be extremely useful to try to reproduce them. And these expressions suggest that the results should be finite and well-defined, and they should match these expressions. So, yeah, I'm not going to explain how this is done. The semi-classical computations is just essentially expanding near minimal surface. In the case of membrane, it's also wrapped on 11-dimensional circle, and we're just computing partition function. So here I just repeated again these expansions written in terms of effective tension. And so this prefactor, which I mentioned, this 1 over sine in the case of ABGM theory, it essentially sums up leading terms at strong coupling, at large tension T, at each order in G string. So this 1 over sine membrane computation essentially sums up all these homogeneous corrections, leading order in alpha prime or leading order in 1 over inverse tension at each order in string coupling. So that's why it's quite amazing that in ABGM theory we have this tool going from membrane to some particular terms of higher order string correction. There's no analogy in the case of n equals 4 Young-Mills theory. So anyway, so this 1 over sine was found as one loop M2 brain computation through one loop M2 brain computation. But again, as I already said, the interesting question is how we can we get from M2 brain this subleading term, which follows from localization, which is 1 over the tension of membrane. So that suggests if that is going to work, there should be some reason for that, that membrane two-loop correction should be ultraviolet finite. There's no a priori reason why it should be. Plus, it should match this coefficient. So there are two other examples where we know what we should expect at two-loop level from membrane. And that's one example is defect anomaly in 2,0 theory. So one starts with AdS7 S4, puts M2 brain there, which wraps AdS3 inside of AdS7, ending on a two-sphere, and free energy in this case captures defect anomaly of 2,0 theory, for which there is a prediction. And the first two coefficients is classical one-loop membrane computations, indeed match these coefficients, but 1 over n term should be two-loop membrane computation. There should be no other terms. So again, that's a challenge to reproduce this 1 over n term. And another example is free energy in ABGM theory. So non-perturbative contribution contains instant-on correction. So that's leading instanton correction, which is 1 over sine. It's one loop contribution, and this classical area. And again, there is a prediction for what should be two-loop computation, two-loop correction. Again, it's a challenge to find it by doing this membrane computation. So I think now let me switch kind of subject somewhat. So the question is whether, do we understand Green-Schwarz string and membrane theory even in flat space well enough beyond one loop order? So we can look at two-loop, particular example is two-loop computation of S matrix on the excitations on a string or on a membrane. In the case of bosonic string, it's kind of this story started with a paper by Dubovsky, Flauger, Garbenko, and then there was a two-loop computation done by Konkin, Dubovsky. And so here you start with Nambu action, expand in static gauge, and look for transverse fluctuations and find 2 S matrix for them. And the result is actually kind of a little bit strange, but it's consistent with what should be, it should be consistent with what we expect from integrability of free string. In the case of Nambu, we expect to get the usual free string bosonic spectrum. And what was done in our papers, we generalized this to Green-Schwarz string and membrane at one loop order and two loop order. So that's what I'm going to review. So that's the usual Nambu action expanded for string or membrane. You can expand in a static gauge vacuum. So it's an infinite string or infinite flat membrane. So I just identify and call longitudinal coordinates with world volume coordinates. You get expansion of the action. So that gives a 4-point vertex. You can compute scattering. 3-level scattering will be just having 3 coefficients A, B, C. So that'll be reflection, absorption, and transmission. And if you want to have integrability, well, in general, they are related by crossing. And integrability demands that should be no annihilation and reflection. So A and C should be 0 in 2 dimensions. Yeah, this is all in 2 dimensions. And B should be consistent with this exponential S matrix. That was suggested by Dubovsky. And then you can check with that S matrix, you match this free string spectrum through, if you put it in TBA. So if you do one loop computation, what you find is that these coefficients A and C are actually proportional to D minus 26. But you can, so that kind of breaks integrability unless you're in D 26. But you can repair this by adding a counter term, which is this Polchinski-Strominger counter term, essentially fixing this anomaly. It's related to the fact that anomaly cancels on in D26, but we can repair this. So anyway, so adding this counter term, you can kill this even in any D. And then one could look at two-loop corrections. So at two loops, you have many diagrams. It's actually very involved computation done on the computer, but these are the results. And these results were found by Dubovsky and Konkin. We first were skeptical what that all means, but indeed we checked that these are correct results. So what you find is in dimensionalization, there is a 1 or epsilon pole. Epsilon is d 2 minus epsilon. So there is a UV divergence apparently, and that's bosonic string at the moment. So then A and C, which should be vanishing, they have imaginary part which is proportional to D minus 26 plus analytic plus real part which is just S4. S is just S variable, kinematic variable. And the B is given by this expression. So everything which you see here is wrong apart from this blue term, which will be consistent with this S matrix, which was somewhere here. Yeah. So S matrix is expected to be just exponent. So if you expand it to this next order, so this term, if you multiply by ST, it will be consistent with this. Well, it should match this essentially after normalization. So what we should expect to say? Well, first we can kill this term if we are in D in 26, or if we include this counter term which I mentioned, and recompute these two-loop diagrams, including this counterterm. So this term goes away. The rest will be real and analytic. So we can add counterterms to kill all the rest. So if somebody, and this divergence happens to be innocuous because there's no log S terms. So this divergence happens to be just artifact of dimensional organization. It's also related to the fact that there are evanescent counterterm which you need to add. So I'm not going to explain this, but essentially this divergence is not an issue. It should be just subtracted. The rest, you should prepare specific counterterms to kill if you want your result to be consistent with integrability. So that is kind of, you don't get integrability on the nose. You need to prepare a particular scheme, and that actually applies to all TT bar story as well. So it's particular prescription which keeps you on the right trajectory, which is consistent with integrability. So at the end of the day, that should be the S matrix, and that's this coefficient which is consistent with this two-loop computation. So what happens in the superstring case? So, so this is Green-Schwartz superstring expanded. If you do the same static gauge computation, fix particular kappa symmetry gauge, there's no cubic vertex, and there is relevant vertices are very simple. So these thetas and x's are these variables, which bosonic part is what was before, but these are new fermionic contributions. So these blue terms do not contribute, they're proportional to equation of motion, they can be redefined away, but the relevant terms are these. So if you compute beta function, you compute this matrix in this case, A and C do not vanish again directly. You need a counter term to kill this term, and that's a feature of Green-Schwartz. It's actually compared to, say, NSR or here you need to be careful because, for example, conformal anomaly doesn't cancel in a similar way as it cancels in bosonic string or in D26. So in D equal 10 here, you need to be more, it's more involved story anyway. But so adding a local real counter term, you kill this term and you get the same result as in the bosonic case. So it's consistent with integrability. At two-loop order, again, there are poles. Again, there are no log S, so the poles are again kind of artifacts of dimensional organization, and the rest story is as in bosonic string. You need counter terms, you need specific counter term, one loop one, which makes A and C zero at one loop. It kills this term, imaginary term. There can't be imaginary term in AC if you, because they can't be killed by real local counter terms, so we must cancel this by adding proper one loop counter term. So that's the end result. So again, result is consistent with integrability. So what happens in the membrane case? So bosonic membrane case, that's one loop, three-level S matrix is the same as in Nambu case, is just a product of two kinematic variables, but at one loop you get something like that, and at, the pole actually survives at two loops, and now it has, there is a log S term as well. So this is the ultraviolet pole is actually proper logarithmic divergence. So bosonic membrane is thus non-renormalizable, and the result looks pretty unpleasant, it's long, and so the conclusion is that you can kill, of course you can kill this pole by adding counter terms, but there's no principle how we should add counter terms. We don't have integrability in this case. At least we don't know if there's any hidden symmetry, unlikely. It is in bosonic string, so that's a story for bosonic membrane. It does have log divergence. At one loop there's none because it's three-dimensional theory, but at two loop there is. So for supermembrane, the story happens to be same, more or less same, but simpler than in bosonic case. So that's an action for this supermembrane. Again, you need to choose particular static gauge and kappa symmetry gauge, and then the action looks relatively simple. And doing two-loop computation, in this case, at one loop you get very simple result, and that was in our paper with Fiona Seibold. It's simpler than in bosonic case, has very nice structure. The strange powers of U and S and T has to do with the fact that there's a factor of dimension, of tension in front. So to match dimensions, you need to have these powers. So essentially it's matrix proportional to tree level one. At two-loop order, we do get the pole, ultraviolet pole. So the conclusion is that M2 brane theory is not finite at two-loop order, which it would be 50-50 guess whether it should be finite or not, but the conclusion is it is not. So what do we learn from that? Jumping back to what I started with, this result need not mean that, say, if we repeat this computation in AdS, and for the free energy expanded near some minimal surface, the result need not be ultraviolet fine. This is just a particular example of flat space S matrix. And S matrix is much more trickier variable than, say, free energy, just where you have no external legs. It's just computing free energies. So we hope still the two-loop computation in membrane theory should give result which is consistent with what we expect from localization. So that's essentially my conclusions. So what I discussed is this examples. We know many examples of semi-classical one-loop computation which match CFT side. The challenge now is to go beyond one loop, and we know a few examples of two-loop computation, but only for the cusp anomaly. But now we hope we'll get also Wilson loop computation in the case of string theory. It remains to do similar computations in the case of membrane and to see finally whether membrane gives finite result and whether it's actually, if it's finite, consistent with localization result. So that seems quite a challenge to the whole AdS CFT program because it must work, but maybe it works in a very specific scheme, or maybe there are hidden symmetries which help us. So thank you very much. Yeah.
Questions?
So, so for M2 branes, I mean, in some you can compactify a circle and turn it into a type 2. So
Type 1.
What happens?
Okay, type 2A. Yeah, sorry. Type
2A, yes. But you can do the same. Have you done? You can do scatter. It doesn't matter. Scattering on doesn't matter if it's 2A, 2B. Right?
No, it doesn't matter.
So,
No.
but what happens to that log, say, at 2 loops if it shouldn't be there in the superstring calculation?
No, it should not. Well, of course not, because the point is, if you do this, say, one-loop computation membrane theory on a circle, so membrane is always wrapped on a circle if we compare to string. So there are extra modes which contribute to everything.
That's where.
Yeah. So that's why one loop in the membrane is actually ultraviolet finite on the nose in the case of Green-Schwarz, while Green-Schwarz has.
Do I understand correctly that you claim that for the M2 membrane, the quantum field theory is non-normalizable, but the S matrix is finite? Is that correct?
No. This particular S matrix which I discussed, S matrix near infinite string, in infinite membrane, transverse fluctuation scattering. What we have shown is two-loop computation gives ultraviolet divergence, honest ultraviolet divergence. Honest means it's a pole plus log S over mu squared. In the case of Green-Schwarz, the same. We just find just the pole, 1 over epsilon, but no log S. And there are known examples of that kind of phenomena, which has to do with evanescent counterterms. And it's a subtle thing, but our point of view is that this divergence should be just subtracted and forgotten. But it would be nice to redo this computation in a different organization to see what happens.
Is there a physical reason why these imaginary pieces pop up, or are they completely unphysical? And is this the reason that you can just put in a counter term and get?
Imaginary parts, if you don't care about integrability, everything should be consistent with unitarity, and in fact it is. But the point which I was trying to make, if you have this imaginary part, you will not be able to cancel it by a real counter term. And that's bad, and then you don't have integrability in particular. And it is cancelled if you preserve integrability at one loop, then these terms do not appear. That's essentially the point.
If there are no further, you want first.
Yeah. So you mentioned evanescent operators. I heard there was a talk where it was mentioned that maybe you can choose a different regularization to make the coefficient 0. Is that regularization known in this case, or?
Yeah, in this case, evanescent counter term is essentially Einstein term in 2 dimensions. In 2 dimensions, total derivative, it gives nothing, but once you move away from 2 dimensions, you get 1 over epsilon r. Yes, but unfortunately, this two-loop computation is very hard to do in your, well, it's, dimensionalization is the optimal for that kind of computations, but in principle, one could try to do it, say, in heat canal or something. Yeah, but that will be very challenging. But that will be settling this question, whether there are logs, there should be, yeah.
Let's thank Arkady again.